Hi everybody. The next section we want to look at is a section about the so-called library functions, and then we'll also look at piecewise defined functions. And I will sometimes refer to library functions as sort of your basic graphs, and the idea in this case is that there are certain functions that we're going to use so often you should just sort of memorize what they look like. I think I've referred to some of these before. So let me just draw the graphs of these up on the board quickly. And then the idea basically is the reason why you want to know what these look like is because graphs of a lot of other functions can be thought of these graphs just as but just shifted left or right or up or down or stretched or compressed or something like that. And so all the library functions are listed basically on page 244 to 245. So let me draw those on the board, and I'll draw sort of a quick sketch of what the graph looks like. The first one your book talks about is the constant function, and I'll just write these in terms of y and not use f of x. But so the constant function basically is just y equals some number. So remember, if you have y equals some number, that just gives you a horizontal line, right, that goes through whatever b is. Another one would be, say, y equals x. Right, that will be the sort of the diagonal line that goes through 45 degrees at the origin. And remember, if you have something more general like y equals mx plus b, that will be a straight line. You have the function y equals x squared. Right, that's your parabola, so that'll look like this. You have y equals the x cubed. And if you forget what these look like, remember you can always just graph them by hand, just make an xy table, but it'd be good to have these memorized. I guess, on the online exams, those are all open book. You can look up information if you want. But on the final, again, I may expect you to have these memorized, or maybe I'll let you bring in a formula sheet with these on there. So don't forget to copy those down to the final. The next one is y equals the square root of x. Again, I think we looked at that the other day. That one will look kind of like that. And then you have y equals the cube root of x. It'll look kind of like this one turned sideways, just like this kind of looks like that one turned sideways, except for the bottom part removed. And then we've got a few more here. I'm running out of room here, but let's see if I can squeeze these in. So you'll get y equals 1 over x. This is kind of a weird looking one. The graph looks kind of like this. And I should mention too that the graph sort of goes out forever this way. So this is what's known as a vertical asymptote. The graph will sort of skid along the line here. And if you think about it, it won't ever be negative over here, because you're plugging in smaller and smaller positive values for x. You're getting 1 divided by a positive number. So the graph will get closer and closer to the x-axis as it moves out that way, but it will never quite touch it. Same thing with the y-axis. It'll go up forever here and never quite touch the y-axis. Same thing here and same thing there. Those are what are known as asymptotes. And then the last function we want to look at is y equals the absolute value of x, and that'll be shaped like a V. So it'll be a lot like the graph of this, except because we're taking the absolute value here, the negative part of this will be flipped up, and it'll go like that instead of going down. Okay, so the idea basically then is if I give you a question on the final, where I give you the rules, like so let's say I give you y equals x cubed and y equals x squared, y equals the square root of x, etc. And then I give you the graphs, you should be able to know them well enough that you can match the rule to the graph. And again, worst case scenario, you can always just, if you forget what does the graph of y equals 1 over x look like, you can always plot points and you'll see that that's what that will look like. But I may limit the use of graphing calculators on certain parts of the final exam so that people with graphing calculators don't necessarily have an advantage over those that don't. So just keep that in mind. So those are your library, your sort of basic functions. So just have those memorized. Now there are a few other things in this section. I guess there's one other function I guess I wouldn't call this one of your library functions, but it's one that you might find useful, especially if you're going to go into computer science, and that is the so-called greatest integer function, and I'll just abbreviate that with GIF. This is sometimes called the floor function or the staircase function, and you'll see why here in just a minute. But the notation for this, there are a couple different types of notation. I guess your book uses the notation int x and then a star. But other notations I've seen before is they kind of put double brackets around there. Basically what this function does is it takes any number that you put in for x and it assigns x the greatest integer that is less than x. So for example, if x is 1.5, that gets assigned a 1. If x is, say, 2.37, that gets assigned 2. If x is 3.98, it gets assigned a 3. So the idea is if you were to graph that, it would look like sort of like a staircase. So that's why it's sometimes called the staircase function. So the idea is 0 itself would get assigned to 0, and then any number between 0 and 1 would get assigned a height of 0, right? So like 0.5 would get assigned a height of 0. So here's 1 here. And then 1 itself would get assigned a height of 1, and then any number between 0 and, between 1 and 2 would get assigned a height of 1. 2 would get assigned a height of 2, and then anything between 2 and 3 would get assigned a height of 2. So you get something that looks kind of like this. Same thing down here. Right, if x is -1, it will get assigned a height of -1, and then any number between -1 and 0 will get assigned a height of -1. So you get sort of a staircase like that. And like I said, this is used a lot in, I guess it's also called the step function, but this is used a lot in computer science when you have to determine like the number of steps to, for example, traverse an array or something like that. So that's one of the places where this is used. All right, so the last thing I want to talk about then are piecewise defined functions. And in a way, this is a piecewise defined function, I guess. But a piecewise defined function is a function that's sort of defined in pieces. So they're sort of like, I don't know, functions with split personalities. They're sort of defined one way on part of the graph and another way on another part of the graph. But let's say, for example, you have f of x equals, say, for example, x squared when x is greater than or equal to 0, and you have that it's equal to x minus 1 when x is less than 0. So the idea in this case then is when x is greater than 0, the graph behaves like x squared. So one thing you can do to graph these is, like if it's helpful to use draw the graph of x squared, but then just erase the part that's less than or equal to 0, because we want the graph of f of x to look just like x squared when x is greater than 0. Okay. And then for x less than 0, the graph looks like y equals x minus 1. So that would be a straight line that has a y-intercept of -1, and it will go through there. Now, because x is actually defined, when x is 0, it's actually defined by x squared. When x is 0, you won't actually get a value for x minus 1, right? But you'll get close enough. I mean, if x is -0.000001, it'll be pretty close to that point. So just draw the graph of x minus 1, which will be a line with slope of 1 and a y-intercept of -1, and it'll look something like that. Now, it may turn out that in some cases the two pieces will actually meet up. Now, in this case, they don't, so you might have gaps or jumps in the graph. But the idea, basically, again, it's called the piecewise functions because it's defined in pieces, right? For the piece, when x is greater than or equal to 0, the graph is defined to be x squared, and when it's less than 0, it's sort of x minus 1. So you can kind of think of these as functions that are put together in pieces, or they're sort of like Frankenstein functions or something like that. And you could have it defined on other intervals other than this. Like you could say, between when x is, say, greater than 5 or whatever, there's another function or something like that. So these can be defined in multiple pieces. All right, well, that's pretty much it for that section. So I hope that's clear. Again, just like usual, if you guys have questions, just let me know, and good luck.